All right, so implicit differentiation. So first thing you're going to do is differentiate both sides of the equation with respect to x. Then you're just going to get all your dy dx terms to one side, factor out the dy dx, and solve. So pretty straightforward. So for something like y squared equals x, if we want to find dy dx, all we have to do first is take the derivative of both sides with respect to x. So on the left side, when we take the derivative of dy dx, or sorry, of y squared with respect to x, that becomes the derivative of y squared with respect to y times the derivative of y with respect to x. That's the chain rule. You're taking the derivative of something that is not in terms of x, but you're doing it with respect to x. So you take the derivative with respect to y and multiply by the derivative with respect to x. Then on the right-hand side, you end up getting just 1, and so you end up with dy dx equals 1 over 2y. Easy enough? Really good there? All right. So same thing here on the left-hand side. If we're going to find dy dx, take the derivative of y squared with respect to x. It's the derivative with respect to y times dy dx. And on the right-hand side, we'll use the quotient rule. So x plus 1 times 1 minus x minus 1 times 1 all over x plus 1 squared. And we'll end up with dy dx equals the x plus 1 minus the x minus 1 should end up giving us the x minus the x will cancel, and the 1 minus the negative 1 will give us 2. So we'll have 2 over 2y times x plus 1 squared. And we can cancel the 2's if we want. Easy enough? Just a quick refresher on this. Everybody good there? Okay. Make sure that when you've got x squared y or xy squared or something like that, that you remember to use the product rule on those. So for this one, we'll take the derivative of x squared y first, which should be x squared times the derivative of y with respect to x. So x squared dy dx plus y times the derivative of x squared, which is 2x. And then same for the other piece, the xy squared, we need to use the product rule again. So that'll be x, and the derivative of the y squared is 2y dy dx plus derivative of x is 1. And so we just have y squared. And on the right-hand side, we should get 0. So that leaves us with dy dx times x squared plus 2xy is equal to negative 2xy minus y squared, or dy dx is negative 2xy minus y squared over x squared plus 2xy. Good or no? All right. On the left-hand side, what should we get here if we take the derivative of x? We should get just 1. And the derivative of tangent y should be secant squared y times dy dx. So we end up with 1 over secant squared y equals dy dx. Or if we wanted to, how else could we rewrite that?
Cosine squared y.
Cosine squared y, exactly. cosine squared y equals dy dx. And that's probably the best answer we can get. Rather have that than over secant squared, but it doesn't really matter. Pretty straightforward, pretty easy. Everybody's good here. All right, I want you guys to find the slope of this circle x squared plus y squared equals 25 at that point 3, -4. So, you guys finished with this one? We need another second to finish it up. Looks like I got some answers coming in, so let's make sure those are right. We got 2x plus 2y dy dx. And then on the right-hand side, we should get equals 0. And we'll note that no matter what the radius of that circle is, obviously the points would change, but going around, these slopes are still going to be at the same angle around. So if we're at the same angle for a different circle, rather than the point 3, -4, we're still going to have the same slope because that radius doesn't effectively matter. So we just end up with dy dx equals -2x over 2y, or just -x over y. Evaluate that at the point 3, -4, and you end up with -3 over -4, which is, as many of you said in the chat, 3/4. Excellent. Easy enough. All right. All right, why don't you guys do this one on your own also. See if you can come up with some reasoning why that the slope must be defined at every point on the graph. That's why there are no places where the slope is undefined. So no vertical tangent lines on this graph. Just to make sure everybody got that when they took the derivative of both sides to start with. And simplify to that, hopefully. And so how do we know that the slope must be defined? Since this equation, 2x over 2 minus cosine of y represents our slope. Yeah, exactly, Adrian. We take our denominator, because the numerator is not going to affect whether it's undefined, but the denominator does. So we take 2 minus cosine y, do it equals 0, get cosine y equals 2, and we know that can never be true because the cosine of any angle is always going to be less than or equal to 1 greater than or equal to -1. So we know that cosine y can never equal 2. Therefore, there are no values of x that make this undefined and no values of y that make this undefined. Easy enough? Everybody feel all right about that? All right. Cool. Now, what if I asked you to find the second derivative of this? So suppose I had dy dx equals, what do we just have? 2x over 2 minus cosine y. And I asked you, what's the second derivative? How are we going to go about that? Yeah, so we're going to take the derivative of this with respect to x to start with, using the quotient rule. Good. So that should be 2 minus cosine y times the derivative of 2x, which is just 2, minus 2x times the derivative of 2 minus cosine y. The 2 goes away, and the derivative of negative cosine is positive sine y, times dy dx, all over 2 minus cosine y squared. Everybody good with that? And then we need to take our dy dx term here and replace it with 2x over 2 minus cosine y. So effectively, we're going to end up with another 2 minus cosine y in our denominator here, because we're going to get a common denominator over here and drop it down. So what we've got to start with is 2 minus cosine y times 2 minus 2x sine y times 2x over 2 minus cosine y, all over 2 minus cosine y squared. Everybody good there? And this is an okay answer, but if we want to be a little more thorough, we could get a common denominator here. So let's do that real quick and turn this into 2 minus cosine y squared times 2. And then we had what, minus 4x squared sine y. And we can now put it all over 2 minus cosine y cubed. Everybody good with that? Okay, let's do one more. So did you guys find the derivative of this one? Find dy dx here. Should get 3x squared plus 3y squared dy dx minus 9. And then we're going to do x times y. So that would be x dy dx plus y times the derivative of x equals 0. And we got a minus 9x dy dx and a minus 9y. We can bring that minus 9y over to the other side. So we'll have 9y minus 3x squared And we got dy dx here times 3y squared minus 9x. And we'll just divide. Any issues or questions on that? Everybody good? Everybody recalls implicit differentiation. Could find the second derivative of any of these if they were asked to. All right. Okay, real quick before we get into the parametric and polar stuff, we're going to talk about the inverse rule for derivatives, which hopefully you remember this is the one that a lot of people messed up last year. The inverse rule for derivatives says that if you have two functions that are inverses that share a point AB or BA, and so if the function has AB or the inverse has AB, then the other function has BA on it, then the inverse's derivative at A is equal to 1 over the original function's derivative at B. You guys remember that rule? Does that sound familiar? Vaguely, says Adrian. All right. Let's see if we can apply it in the situation. Hopefully that will refresh your memory. Okay. So if we have f of x equals x cubed, and we know that g is the inverse function of f, and we want to find g prime of 8. Okay. So that tells us that g contains a point 8 comma something, which means that f contains a point something comma 8. So what point is something comma 8 for f of x? F of x should be 2 comma 8. Okay, so we could write that's 8 comma 2. And from there, we should know that if we're looking for g prime of 8, it should equal 1 over f prime of 2. Okay? And so we should be able to find f prime of 2 right here. F prime of x is just 3x squared. If we evaluate that at 2, we end up getting 12. So g prime of 8 ought to equal 1 over 12. Does that seem familiar now? Okay. So our rule is, and I'm going to write the rule out on another slide because that other one I think is a little convoluted, that if f and g are inverses, and f has the point AB, then g must have the point BA, and f prime of A is equal to 1 over g prime of B. Everybody good with that?
Oh, yeah, for sure.
All right, that's it for implicit and the inverse rule for now. So what we're going to do is we're going to move in and start talking about parametric and polar functions. Our goal is to be able to find the derivative dy dx of a parametric, which is x equals some function of t and y equals some other function of t. Okay. So what we want to try to do is we want to try to eliminate the parameter in one of the equations to turn it into y equals capital F of x. If we can do that really simply, then it should be really easy to find dy dx, right? We can just take the derivative of that capital F of x function. Do you guys agree with that? Okay. So that's one way that we can go about it. The other way that we can go about it is just by thinking about what does dy dx mean in this case using the chain rule. Okay? So if we were to take the derivative of
Mr. Bachelor?
Yeah.
I think you stopped screen sharing.
Oh. Oh, that's why there's like 6 things in the chat, and it's, yeah, that makes sense. All right. Let's see here. Is it back on?
Yes.
Ah. All right. Sorry about that. Okay. So let's try this again. So if we could eliminate the parameter in one of them, we could then just take the derivative of it if we could get it all into one variable. But if we can't do that, how do we take the derivative of y? Let's say, how would we find the derivative of y? Well, it would just be dy dt. Right? So dy dx should just equal dy dt divided by the derivative of x dt. And you can see the dy dt and the dx dt, the dt's just cancel. Right? So you just end up with dy dx equals basically just dy dx. So if it's not simple to eliminate the parameter in one of the equations and put it into one regular function, all you have to do is take the derivative of each of them with respect to t and find the quotient of them. Take the, divide one by the other. So we're going to go ahead and do that real quickly with a couple of these, starting with a nice easy one here. X equals t to the 5th minus 4t cubed and y equals t squared. So if we're looking for dy dx, all we have to do is find dy dt, which is what? What's dy dt? Just 2t, right? And our dx dt should just be 5t to the 4th minus 12t squared. And we can just simplify out the t's there and get 2 over 5t cubed minus 12. Easy enough.
Mr. Bachelor?
Yeah.
Why is it still like in terms of t?
Squared. Sorry. Yeah, so that's okay. And in fact, that's even more convenient for a parametric. We want to still be in terms of t because, if we're looking at this and we're saying, well, what's the derivative of this? And all of these values are in t, and we have some parameter t, like, t is greater than 0 or something like that. And so we're looking at these all in terms of t. So to have the derivative in terms of t is more convenient because if we want to know what the slope of the tangent line to the function is, it's nice to know at what t value we plugged into these equations and what t value, that way it's the same t value for the derivative rather than having an x value for one and a t value for the other. But yeah, it's always going to still be in terms of t when we do this. Does that help or no?
Yes, thank you.
You're welcome. All right, you guys do this one real quick. So what's dy dt here?
So I only include them if they like separated.
Just cosine t, right? Good. And what is dx dt?
But having it in its own
Should be 2t plus 1 over 2 root t plus 1 over 2 root t. Easy enough?
Yeah.
Pretty simple, pretty straightforward, I hope.
I don't think they have. I'm not sure.
All right, let's make sure we remember how to take the derivatives of some of these other functions now. So let's find dy dx for this one. What's dy dt going to be?
Cool.
Got to use the chain rule on it, right?
Yeah, what's yours?
Yeah, cosine t times e to the sine t. And then in the denominator, derivative of natural log of u is 1 over u, so 1 over t cubed minus 2 times the derivative of t cubed minus 2, so 3t squared, which is going to give us t cubed minus t times cosine t times e to the sine t over 3t squared. Good or no? And if I said, what's the slope of the tangent line for t equals 1? Well, all you do is you plug in t equals 1 and get some number, or t equals 5 or 2 or something like that. Find the slope of the tangent line. Good? Easy? Okay. Let's see if we can find the second derivative of a parametric function. So anybody have thoughts on how we're going to go about this? Yeah, so what we're doing is we're taking the derivative of our original derivative, right? We're taking the derivative with respect to x. So if we want to take the derivative of this, we need to take the derivative with respect to x of this, right? That's what the second derivative would be. It's always with respect to x. So what we're doing is we're taking the derivative of something that is in terms of t. And so in order to take the derivative of something that's in terms of t with respect to x, we have to first take the derivative of it with respect to the variable t, right? So what we're going to do is we're going to take the derivative with respect to t of dy dt over dx dt. And then, according to the chain rule, if we take the derivative with respect to t of the thing, then we have to multiply it by the derivative of t with respect to x, which looks a little bit weird, right? We don't really have dt dx, but that's what we should have, right? If we want to take the derivative of our function with respect to x, we got to take the derivative in its variable t and multiply it by dt dx. And we could flip this dt dx around and make it a division. So what we're going to do is we're going to take the derivative with respect to t of dy dt over dx dt and divide this by dx dt, right? Because dividing by dx dt is the same as multiplying by dt dx. So effectively what we've got is the derivative with respect to t of our original derivative divided by the derivative of x with respect to t. So yes, Darius, we're using the quotient rule, so we'll have to use the quotient rule generally to find the derivative with respect to t of dy dx. but then we're going to have to remember to always divide that by dx dt. Everybody okay with that or no? Any confusion on that? Because usually every year that confuses people, and I'm sure now that we're not in person, it's probably even more confusing. Sure. So we want to take the derivative with respect to x of our derivative, right? That should give us the second derivative. So the second derivative of y with respect to x is the derivative with respect to x of dy dx, which means we're taking the derivative with respect to x of dy dt over dx dt. Well, if we look back at the original problems that we were doing, dy dx or dy dt over dx dt is always in terms of t. Okay? And so if we're trying to take the derivative with respect to x of something that is in terms of t, the way we do that is we break that down to become the derivative with respect to t of those things in terms of t times the derivative of t with respect to x. That's the chain rule part. So this right here is the chain rule. And that's, I think, the part that gets a little bit confusing, is that we got to make sure we use the chain rule. Does that make more sense now, Delphine, to that point? And everybody? Okay, cool. And so then since we're multiplying by the derivative of t with respect to x, that's the same as dividing by the derivative of x with respect to t. Just flip that around, make it a division, and we end up with this formula, which is how we will take the second derivative of a parametric. Any other questions on that before we move on and do that? All right, let's do one then. So I think this is one we already did earlier, right? We found the first derivative of this, t to the fifth minus 4t cubed over y equals t squared, right? Is that the same? Yeah. So what was our dy dx there? Dy dx was equal to 2 over 5t cubed minus 12t. That's what we had before, right? Okay. So from there, we want to find the second derivative. We have to take the derivative of this with respect to t. And for this, we can use the reciprocal rule. So might as well. Same as the quotient rule, right? Reciprocal rule says that this is the opposite of the derivative of this, which is 15t squared minus 12 over 5t cubed minus 12t squared. Right? That's the that's the derivative with respect to t of dy dt over dx dt. And then we have to divide that by dx dt. And so dx dt is what? It's 5t to the fourth minus 12t squared. And so we could simplify this down to become negative 15t squared minus 12 over 5t cubed minus 12t squared times 5t to the fourth minus 12t squared. And if you wanted to, you could take a t out of that one in the denominator there and put those together, but not necessary if you don't feel like it. Any issues with that? Yeah, no problem. So we took the derivative of, so we originally, this is the first problem that we did earlier today, Luke. So we already had the derivative from right here. The derivative with dy dx was 2 over 5t cubed minus 12t. That was from the first problem, same parametric function. So to find the derivative of this with respect to t, we use the reciprocal rule. So reciprocal rule, oh, shoot. I went through and did my whole reciprocal rule and forgot to include the 2 up there in the numerator. So our reciprocal rule says that whatever this numerator is, as long as it's constant, can stay there. And then we have negative derivative of the denominator, negative g prime. Call it g, that's what we normally use. Negative g prime over g squared, that's the reciprocal rule. So there's negative g prime, 15t squared minus 12 over g squared, that's the denominator squared. And then we keep the 2 up there. And then we have to divide that by the our dx dt, because that's what our second derivative with respect to x of a parametric is, right? It's dy dx with respect to t differentiated again, divided by dx dt. And dx dt is 5t to the 4th minus 12t squared. And so then we just drop this denominator with this denominator and put it together as a single fraction. Does that make more sense? Or is that still confusing? Good. Okay. Anybody else? Everybody okay there? All right, cool. Let's do another one. Why don't you guys do this one on your own? So just to make sure, what did you guys get for dy dx? Dy dt should have been negative sine of t plus 2. And dx dt should have been what? 2 sine t times cosine t? Yep, exactly. Which we could, if we wanted to, just to make our lives probably a little more simple later on, is 2 sine t cosine t can be rewritten as what? Yeah, sine of 2t, exactly. So now what we're going to do is we're going to take the second derivative. So we're going to take the derivative of this with respect to t and then divide it by our dx dt value. So the derivative of this should be what? Should end up with sine 2t times the derivative of negative sine of t plus 2, which should be negative cosine of t plus 2, minus our negative sine t plus 2, which will give us a plus sine of t plus 2. And derivative of sine 2t should be 2 cosine 2t all over sine of 2t squared. And then we have to divide that by dx dt, and dx dt we already know is 2 sine t cosine t, or sine 2t. So really this becomes a sine of 2t cubed. Good or no? Any issues or questions with that? So Shayla, we're dividing, once we've done our quotient rule, we're dividing by dx dt. Yeah, so again, I'll go through it again. So numerator is quotient rule to start with. So v sine 2t du negative sine t plus 2's derivative is negative cosine t plus 2. And then u dv should be negative sine 2t, but since it's a minus, we made it a plus sine 2t plus 2. And then derivative of sine 2t is 2 cosine 2t divided by sine of 2t squared. I know I have a cube there, but we divide by sine of 2t squared. That's all the quotient rule part. And then, because of our rule for this, we said that the second derivative with respect to x has to be, once you've done your derivative of dy dx with respect to t, you have to divide it by dx dt. And so dx dt, we already found to be 2 sine t cosine t, or sine 2t. So rather than have a sine 2t squared from our quotient rule, we're going to have a sine 2t squared times a sine 2t, which becomes a sine 2t cubed. Does that make more sense or no? Does that help? Or Nikki, you're good with that also? Okay. Anybody else have an issue with that, or everybody okay there? All right. I'm not sure why I have a blank page here. Does that page look blank to everybody else? Yeah. All right. I don't know what happened there. Get rid of that. All right. Last one of these. You guys give this one a shot on your own again. And then we'll go through it. All right, how are you guys doing with this one? What'd you get for just dy dx? Should be 2 secant squared 2t for dy dt. You guys agree with that? Okay. And then for dx dt should be 1 over 3t cubed plus 5 and times the derivative of 3t cubed plus 5, which is 9t squared, which should give us, if we want to rewrite this, 3t cubed plus 5 times 2 secant squared 2t over 9t squared. Everybody agree with that for dy dx? Okay. You guys still working on the second derivative, or should I do that now? No response. Does that mean it's time to do it or no? No? All right, take another minute or two and try and get that second derivative. All right, that's fine, yeah. If you're still working, just tell me that and I'll give you more time. Yeah, take another couple minutes and try and figure that out. It's gonna get a little bit complicated.
Mr. Bachelor, you're muted.
Yeah, I know. I was just starting to write it out so that I wasn't disturbing anybody, but figured I'd give you guys a chance to keep working on it. But now that you've mentioned it, I'll just ramble on like I usually do. Let's see here. There's the first part of my numerator that I definitely don't have room to write the second part of it, but that's my v du minus, there's my dv, and I gotta have a u in there. Let's see, I'm just gonna circle this and put it there, because that's all the room I have. All divided by 9t squared, so 81t to the 4th. And then we have to divide again by dx dt. And what was dx dt? Dx dt was this piece right here. So if I'm dividing by this fraction, I'm going to multiply by the reciprocal of it. So 9t squared and a 3t cubed plus 5. So that's a little bit of a mess. First off, cancel this and this out. And if we try to write this out, we'll get 3t cubed plus 5 times 3t cubed plus 5 times our 4 secant squared 2t tangent 2t plus our 9t squared times 2 secant squared 2t minus 18t times 3t cubed plus 5 times that 2 secant squared 2t, which now has become impossible for you to read, over 81t to the fourth. All right, let me answer that in just a second. Everybody okay with that? It's a little bit of a mess, but yeah, an 8. Did I miss a 2 in there? Let's see here. I might have missed a 2. Let me see. We're taking the derivative of, well, we were taking the derivative of 2 secant squared 2t, right? So that should be 4 secant 2t. Yeah, it should be an 8. You guys are right. You guys are right. That should be an 8. Alice, let's see, how did I cancel the 9t squared? So I had a 9t squared out in front of this whole, this was, that's not in front of the whole thing, is it? Yeah, you're right. I shouldn't have canceled that 9t squared. Because that 9t squared is just in front of the first part of it. Oh, I made a mess of this. This is what happens when I'm on this tiny little laptop screen. Okay. Here's what we're going to do. Yeah, let's see if I can just, in fact, we'll just erase this right there. This is now a 9t squared, and this still has a 9t squared in it. And this shouldn't have been canceled. So sorry about that. I won't give you any more that are that in-depth on this. They'll be easier than that, hopefully. A lot of a mess in there. Yeah, no problem, Nick. Yeah. We get the idea, though, of what we're supposed to do. That's the important thing, is we understand conceptually how to take the second derivative of a parametric. Anybody have an issue with that concept? Okay. Everybody's good there with the idea of second derivative of a parametric. Okay. Right. So let's see if we can do polar. We got a few minutes left here, right? Yeah. So we have a polar function, r equals something in terms of theta. We should very easily be able to just split this up so that we know what x is and we know what y is. X should just be r times cosine theta, so cosine theta f of theta, and y should be r times sine theta, so sine theta times f of theta. Do you guys agree with that? Nick, I'm not sure what you mean by 14. Oh, we have 14 minutes left. Is that what you're trying to say? Okay. I got you now. All right, so everybody good with we could rewrite x and y as this, cosine theta f of theta and sine theta f of theta? Right, x is r cosine theta, or x is r sine theta, right? And so then, what does this look like now? This just looks like, what kind of function does this look like? With any luck, it should look like a parametric function, exactly. It should look like a parametric with a parameter of theta. And so in order to figure out what is dy dx should just be the derivative of y with respect to theta divided by the derivative of x with respect to theta. The same idea as what we were doing with the parametrics before, right? And if you were to take your r cosine theta and your r sine theta and actually do that derivative, you will always end up with this: dy dx equals dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. That's just by using the product rule on each of these. But I think it's probably easier than remembering that formula is just to remember that x is r cosine theta and y is r sine theta, and to find dy dx, just take the derivative of y with respect to theta and divide it by the derivative of x with respect to theta. Good or no? These ones get pretty convoluted and complex too, because your r cosine theta and your r sine theta pretty much always have the product rule already built into them when you're doing all these derivatives, so they get to be a little bit of a mess. So let's see if we can do this one. We have r equals 3 sine 2 theta. So what does x equal? X should equal r, so 3 sine 2 theta times cosine theta, and y should equal 3 sine 2 theta times sine theta. And we should be able to use those to figure out what dy dx is. Dy dx should be dy d theta, so what's the derivative of y with respect to theta? It should be 3 sine 2 theta times the derivative of sine, which is cosine theta, plus our sine theta times the derivative of 3 sine 2 theta. So the derivative of 3 sine 2 theta is 6 cosine 2 theta times the sine theta. Everybody good with dy d theta? Okay, and dx d theta should be 3 sine 2 theta times the derivative of cosine, which is negative sine theta, and plus derivative of 3 sine 2 theta is still 6 cosine 2 theta times cosine theta. If you want to divide a 3 out of all of it, but you don't need to. Same basic idea, just have to write your own x's and y's from the polar function that you started with. Everybody good with that? Any questions on that? Any issues with that? All right. Let's do another one. What should x be? X should be r cosine theta, and y should be r sine theta. Everybody agree with that? Yeah, no, maybe. Okay. And so dy d theta, dy dx, which should be dy d theta over dx d theta. So we'll get 3 plus 2 sine theta times the derivative of sine, cosine, plus our sine theta times the derivative of 3 plus 2 sine theta, which is negative 2 cosine theta, all over the derivative of x with respect to theta, 3 plus 2 sine theta times the derivative of cosine, which is negative sine theta, plus our cosine theta times the derivative of 3 plus 2 sine theta, which is still negative 2 cosine theta. Everybody good there? Any questions or issues with that one?
For the like when you're doing the derivative of like the 2 sine theta, how did you get the negative 2 cosine theta? If that makes sense.
Of the 2 sine theta?
Like why is it negative?
Yeah, that's, I don't know, good question.
Oh, okay.
I don't know why that's negative. It's not. Probably because I'm losing my mind being at home trying to teach with my children. Any other questions on that? Or is that good now? All right, let's do one more. You guys try this one on your own.
Are you going to the dogs too? Yeah, right, people.
So we've got x equals 2 cosine 3 theta cosine theta. And we got y equals 2 cosine 3 theta sine theta. Everybody agree with that? I know you're not done with this yet, but. And our dy dx should then be what? Dy d theta should be 2 cosine 3 theta times the derivative of sine, which is cosine, plus the derivative of 2 cosine 3 theta, which is, try to do it right this time, negative 6 sine 3 theta times the sine theta. And then our dx d theta should become what? 2 cosine 3 theta times the derivative of the cosine, which is negative sine theta, plus the derivative of our 2 cosine 3 theta, which is negative 6 sine 3 theta, times the cosine theta. And again, you can divide by the 2's if you want to. But is that what you guys all got? All right. Any issues with the polar derivatives finding dy dx? Looks like I have another blank page, so I guess we're done. So we're going to apply some of this stuff to finding tangent lines and figuring out when these things have horizontal and vertical tangent lines, or figuring out when they're undefined, find like cusps on polar graphs and all of that. We'll do that more later this week, and also in the applications, we'll start talking about applications of the derivative. But those are the basics of how to find derivatives of parametrics and polar. They get a little bit messy, but they're not too bad overall. Hopefully that all makes sense. I'm going to post up an assignment in a couple of minutes. It will be due at the end of the day today. It's got a couple of the polar, a couple of the parametric, and a couple of the implicit. Shouldn't take too horribly long, I hope. If you have questions on it, just let me know.